Water, the most basic and crucial element of life. It might sound shocking to you knowing that 1 in 9 people do not have access to safe water, and around 6,000 of children die from water-related diseases every single day. The developing and low-income countries are the ones mostly dealing with this problem since they lack the required infrastructure and specialty in water and wastewater treatment. Having said that, water shortage is a global problem shaping on the human's future on this planet, so we need innovative and sustainable solutions more than ever. Membrane-based technologies offering the advantage of simple implementation and operation have a privilege over other methods. Membranes purify water by acting as a barrier and retaining pollutants while passing water molecules. However, after a while, pollutants start to accumulate on the surface of the membrane, decreasing the water permeability. Immobilizing photocatalysts on the surface of the membrane and initiating a photocatalytic degradation of pollutants using UV radiation would be a proper answer to this problem. UV acts as a source of energy to excite and activate a photocatalyst, a particle with the ability to absorb light and provide a base for starting chemical reactions. Nonetheless, due to the size and shape restrictions of UV lamps as the primary source of UV, the solution was not practical until now. With the emerging of the small-sized UV LEDs offering the flexibility to be implanted in the existing membrane modules without further modifications, we are now able to think of having photocatalytic membrane reactors on a large scale. The next obstacle in scaling up the technology is developing a highly durable photocatalytic membrane as well as enhancing the pollutant removal efficiency. The main objective of my thesis was to properly address these problems. We successfully developed a novel synthesis which led to a highly stable attachment of photocatalyst particles to the membrane surface, as well as higher removal efficiency compared to commercially available photocatalyst samples. Then, to optimize and study the potential of UV LED coupled photocatalytic membrane reactors, we designed a laboratory scale apparatus operating in conditions similar to those of industry. These promising results made us believe that developing a photocatalytic membrane with antibacterial and antifouling properties, coupled with the amazing features of UV LEDs, can make a breakthrough in the membrane systems and pave the way towards a world in which everyone has access to clean water.